This video is brought to you by the ILC. Whenever we're given constants that have relationships and the rates that relate them, we're probably dealing with what's called a related rates problem. So a related rates problem usually has some sort of picture or at least an equation that relates some constants or some variables, some numbers that are going to be changing, and time. So here, for instance, we have a house with a 15-foot ladder lying against it. There's our ladder. The base of it is sliding away, however. Right, so this distance right here, we have the ladder sliding away. By the time the base is 12 feet from the house, the base is moving away at a rate of 18 feet per second. So let's interpret all these things first. The ladder is 15 feet, so that means the distance from here to here, in other words, the hypotenuse of this right triangle I've just drawn, is 15 feet. That number's not changing. So the ladder isn't going to shrink or expand at any point during its sliding away from the house. However, this distance right here, its height along the house, and this distance right here, the width of the base here, the distance from the distance of the base from the base of the house, is changing. So let's give them some variables, maybe A and B. And I use A and B because we know that this is a right triangle because the house isn't leaning in any direction, presumably. So that means we can create the relationship a squared plus b squared equals c squared. And of course, c squared, c is 15, is 225. Now they give us some other numbers, and you see by the time the base is 12 feet from the house, the base is moving away at a rate of 18 feet per second. So I want to write those down somehow. I noticed that the base here, the time the base is 12 feet from the house, so b is equal to 12, is not a constant. Right? The base is sliding away, so it's 12 feet from the house at a certain snap in time. We can take a picture at a certain time and the base will be 12 feet from the house, but that's only at a certain time. That number is going to change. In other words, at a certain instant, so I'm going to write instant over here, the base b is equal to 12. At that same instant, the base is moving away at a rate of 18 feet per second. So I know dB dt, since it's moving away, it's getting larger, so a positive 18. So why did I know all this stuff? Well, 18 feet per second, b is measured in feet, right? Because all these measurements are measured in feet. This is 15-foot ladder. dB then represents a change in feet, and dt represents a change in time. So we have feet per second. So this is a dB dt, this 18 is. I say b because it's the distance the base is moving away. Now I don't know at any other time what speed the base of the ladder is moving away from the house. So what I have to do is just assume that at that instant it's equal to this. Now I have b is equal to 12. You may ask yourself, why don't I just take this and plug it right into there? Right into that b. But that would actually be a mistake. We couldn't do that. And the reason we can't do that is because this b, like I mentioned earlier, is changing. It's only b equals 12 at a certain instant. If I were to substitute the 12 into here, then that would assume it's 12 all the time, no matter what. But it's not always 12. So how can I substitute the 12, and how can I substitute this 18? Well, I noticed dB dt, that kind of gives us a hint that we need to take a derivative. And that's, after you take a derivative, that's when you can substitute your instant values. In other words, dA, when I take the derivative of this equation, I'll end up with 2a dA dt. Notice that whenever I take the derivative of a variable, I multiply by d variable dt. And then the same thing for b here, 2b dB dt equals derivative of 225. 225 is a constant, so it's equal to 0. I noticed that all of these have 2 in front of them except for 0, but that's not going to matter because when I divide by 2, the 0 is not going to change. 2's all go away, and 0 is going to turn into 0 here, so I don't really need a slash through that. What I end up with, at least so far, is dA dt plus b dB dt. That's equal to 0. So once we have all this established, you might be asking, why are we doing all this? What's the point? And we want to answer these two questions, and let's take a look at these. So find the rate at which the top of the ladder is sliding down the wall at that time. So that time meaning the time that the base is 12 feet from the house and the base is moving away at 18 feet per second. However, I noticed that we actually already have a variable for that distance that the ladder is on the wall, right? The distance from the ground, and that is it's a. So what we're trying to find for part A is dA dt. I want to solve for dA dt in this equation. So I can substitute b, because I took the derivative. I can substitute dB dt, because I already know that. However, I would still have this a floating around. So if I'm trying to solve for dA dt, I would still have the a, and that's a problem. So we need to find that a somehow. Now I mentioned earlier that we can only substitute this b into our equation when after we've taken the derivative. But that's only true if we're talking about an instant. We can substitute it earlier if we know we can use it for a specific, to find another specific variable, and then just toss that equation away. Like we don't care about it anymore. For instance, here I can say, let's put a box around this instant so I know I don't have to touch it anymore. I want to find out the a value at b equals 12. All I have to do is substitute b equals 12 into this equation here, and that can tell me my a. A squared plus 12 squared, so 144, equals 225. All right. Next, we'll subtract 144, and with a squared equals 225 minus 144. When I get a calculator out and perform that subtraction, 225 minus 144, I get 81. A squared equals 81. Since a squared is equal to 81, a is equal to 9. Notice I would normally put plus or minus 9, but because we're talking about a distance here, I only care about the positive version. Alright, now I can substitute a, b, and dB dt. So think of this a equals 9 as another instant value here. Alright, so I have 9 dA dt plus 12 dB dt, or dB dt we also have a variable for, a number for, that's times 18 is equal to 0. When I subtract, I'll have negative 216, and when I divide, I get 216 divided by 9, which is 24. However, there's this negative, so it's negative 24. And you may be looking at this and starting to panic a little bit because we have a negative number in there. But that's fine, actually. Notice that the ladder is sliding down the wall. That makes sense then that the change in A, the distance from the ground to the top to the ladder here, is shrinking. In other words, it has a negative derivative. So it makes sense that dA dt would equal negative 24, and we put feet per second. Alright, that solves part A here. That's the rate at which the top of the ladder is sliding down the wall at that time. How about part B? It says find the rate at which the angle between the ladder and the ground is changing at that time. So first of all, what is that? And look at this picture again. The ladder and the ground would be this angle right here, which we'll call theta. We like theta for our angles. How can I create a relationship between the things I know, these instant values, and theta? Well, the instant values are b and some other relationship with b, dB dt, right? The derivative of it. And I know if I can create a relationship between that and theta, that will work. And I notice adjacent over hypotenuse would be cosine of theta has to equal b over 15. This part's actually a little bit easier than the first part. Because when I take the derivative in order to find the rate at which the angle of the ladder is changing, I take the derivative, I find negative sine theta d theta dt is equal to 1/15 dB dt. I like to think of b in the numerator here as being multiplied to 1/15 on the right. So I think of 1/15 as a coefficient. And that's how I take the derivative to find this. Here we run into a similar problem we ran into with the last one. We have a certain number of variables. We have here theta, d theta dt, and dB dt. D theta dt, so let's get this scrolling working. dB dt is something we know, it's 18. And d theta dt is actually what we want. It says find the rate at which the angle is changing at that time. However, sine of theta, or theta, we don't know. Now let's try and find theta, or at least sine of theta. I'll show you what I mean. So let's redraw this triangle, just so I have it down here as well. There's 15 over here, and b down here, a over here, with theta here. Now I'm going to find theta. Now at that instant, notice that this theta is changing over time, so only at that instant is it going to have a constant value. Now we have a couple of ways of doing this. I know that b is 12 at that time, so I can just say equals 12 just for this exact instant here. However, if you notice, if I take a cosine inverse in order to find theta, because I can say cosine of theta is equal to 12 over 15. All I did was substitute b into this equation over here. I would have theta is equal to cosine inverse of 12/15. And then I would have to take this cosine inverse and plug it into the theta here in order to find sine of cosine inverse of 12/15. So this is getting complicated. I want to avoid that. And here's how I do. Well, instead of substituting theta, let's substitute the entirety of sine of theta. I know that b is equal to 12, but I also know at that instant that a is equal to 9. This is the number we figured out earlier on. Right? We figured out that a is equal to 9 at that instant. That means that sine, opposite over hypotenuse, is 9/15. And that's a number we can simply substitute into this equation here. I have negative 9/15 d theta dt is equal to 1/15 times 18. Oops, let's get that 18 a little better. 18. And this is just arithmetic from here. So I multiply by 15, divide by 9, and I believe what I'll have is d theta dt is equal to probably -2. And since my original measurements in theta should be measured in radians, we just assume radians, especially when we're talking about derivatives here, then this would be 2 radians per second. -2 radians per second. And this makes sense that it would be negative as well, because the ladder is falling down the ladder is falling down the wall here, and that means this angle is becoming smaller. Now that we've answered both part A and part B, we're done.